So today we're actually going to start a new topic, which will stay for at least a week or so, and this is the topic of streaming algorithms, um, which is an area with many nice applications of randomization. So let me give you sort of the simplest setting that we're going to talk about. And so we consider a universe, or consider a universe n. So this is a universe of items. And so when I say item, I typically mean an element from the universe. So items appear as a stream of input, and the algorithm processes elements, or I said items, in stream order with limited memory. So formally, we can think of the input, as an array of length m, and this is an array of items in n. Right? In the algorithm, a streaming algorithm processes the array using typically a single or constant, passes over the input array. So pictorially, you can think of, here's your input array. It has a collection of elements, so on and so forth, and your algorithm kind of passes over the elements one by one. It has some limited storage here, which is typically the storage we typically assume is much smaller than m or n. So the algorithm cannot afford to store the entire input array, which is the stream, nor can it actually afford to store the universe. And this is of increasing applicability to this is often referred to as a big data model, because it tries to capture some of the challenges in algorithmics for large data. And it is, it has been studied for maybe a few decades, but increasingly there's more and more interesting and challenging research here. And I'll actually talk about some algorithms which are widely used in practice. So are there any questions about what the model is? So again, you have an array, and you should think of the array as it's an array of items, or one can just think of numbers in some fixed universe. The algorithm makes a single pass over the array, and as it passes over the array, it gets to, it would store something, some data structure, and in the end it has to then decide some property, answer some questions about the array. And so we will look at the fundamental problem, one of the oldest problems studied, classic fundamental problem of counting the number of distinct elements seen. I should say, given this model, we don't have a notion of decrementing an object, decrementing an item. So you should just think of, each item appears some number of times and that count only increases. This is referred to as the cash register model. And but as we go on over the next couple of lectures, we can get more into models. Right now, I would just want to look at the simplest problem. So your array has a collection of items, and you want to count the number of distinct elements, distinct items that are seen. So does the question make sense? Any questions about the question? Right, so it's a really simple problem. So obviously, if you could store the entire array, then it's easy. You would just build a hash table or any dictionary data structure. And the question is how to do this with memory much smaller than m or n. It's trivial how to do it with a memory of n. You could actually not even, you don't even have to store a hash table. You could just store a bitmap, right? So with a bitmap, n bits suffice. Now, this sort of assumes that you know what the universe is. And if the universe is unknown, then you could try to do some kind of hash table, some data structure. But fundamentally, the storage here will be at least n bits. The question is, can you do better? And as we discuss this, we're actually going to try to count things at the bit level, because that is going to be important for the analysis and the applicability of these algorithms. So I'm going to this is an interesting topic also, because there is a theory versus practice gap here, and one that has been somewhat controversial. So let me give two models here. So this is the more realistic model, and it's two models of randomness. The more realistic model is to assume there exist truly random hash functions. And the practitioner, this is a practitioner would say just use a cryptographic hash function. You could use a cryptographic hash function. The theory viewpoint is the algorithm can only generate random bits, because the theorist would say the construction of hash functions is itself challenging, and it requires additional storage, etc. So the point is, if one looks at cryptographic hash functions, we don't have any provable guarantees on it, and therefore the pure theory viewpoint is to say that the algorithm can only generate random bits. The more realistic viewpoint, which still, would still require significant algorithmic thinking, is that there exist truly random hash functions, such as cryptographic hash functions. And so we might as well assume that there exist such hash functions, because this will make many of our problems much easier. And in the theory literature, you will see a significant amount of work done to overcome these assumptions. And this is a bit of a controversial point in the sense that these extra work and the extra algorithmics required to remove these hash functions often make the algorithms impractical. And so most of the practical algorithms, which also have interesting math associated with them, come from assuming the more realistic assumption. And so for today's discussion, I'm going to stick with the more realistic model. And in the next lecture, I'll tell you on the kinds of tools people use in theory to remove those assumptions. Although there is one school of thought that it is not really necessary to do so for designing algorithms. So let's start with the realistic model. So hash functions exist. By hash functions, I mean truly random hash functions, and we'll discuss what exactly I mean by that. So we want to count the number of distinct elements. And this number is obviously its at most n, which is the size of the universe. So to store n, or an approximation, requires log n bits. Just to store the actual number. And you should think of n being astronomically large. Like n might be like, in the billions or so. How can you do better than log n? And this was this amazing idea, which was first given by Morris in 1977, but it was described just as an approach, and it was really analyzed in detail by Flageolet and Martin in 1985. And what Morris had suggested, which Flageolet Martin built on, is to get an estimator for log n. So don't try to estimate n, estimate log n. And this, or I should say maybe technically over here, instead of log n, I'll say the natural log of n, but it's, for our purposes, we'll see that, we're not going to get into that distinction as of yet. So let's just say you want an estimator of log n, or lg of n. So by the way, I should specify that by lg, I mean the log base 2. Now, to get an estimator for log n, to store this requires only log of log n bits. Or I should say log of the natural log of n, but this is only going to add a constant. And again, this is important for the practical applications, but for now, let's just think of everything being log base 2 for simplicity. So the amazing idea is, instead of trying to estimate the number of distinct elements, you try to estimate the number of, I should say, log of d, where d is the number of distinct elements. And this is going to require at most log n of bits, because... So is this clear? This is a very important and amazing idea, that instead of trying to get an approximation for the number, try to get an approximation for the log of that number, and that can be stored in log n bits. So this is amazing, right? This is saying that if n was 2 to the 32, which is billions, you only need essentially like something like 5 bits. Of course, this is going to give an approximation. but it's only a 5-bit sort of storage. Okay, so now this idea is referred to as approximate counting. It has a bunch of names. It's also called probabilistic counting, which I believe is the name given by Flageolet and Martin. And it is the basis of an algorithm that you may have heard of. It's referred to as the loglog algorithm. And since then, Flageolet, Martin, and others, and many of his collaborators have come up with algorithms with loglog. They've come up with something called the super loglog, and then there was something, the most recent, which was called the hyperloglog. And the hyperloglog has had an immense impact in the practice of many of these techniques, so much so that most companies implement their own hyperloglog algorithm. So I'll talk a little bit about the hyperloglog, although the analysis of the hyperloglog is sort of well beyond the content of this course. Okay, so let me now give you the idea. Yes.
Like, are there really applications where you care about like 32 bits versus 5 bits?
Oh yes, because you'll see that essentially this 5 bits is sort of, it's going to have some kind of, this is a randomized count, so there's going to be some variance. So to cut down the variance, you need to repeat the sketch. And then that repetition means you may need to repeat this 1,000 times. So repeating 32 1,000 times versus repeating 5 1,000 times is a big improvement on space.
Sure.
And you can essentially construct, I myself have used these in practice, and it's a very common technique that, let's say you see a bunch of IP addresses coming through a router, and then you want to sort of store how many distinct IP addresses that have been seen, and the hyperloglog is used, or like the number of distinct users who've interacted with some system. Typically, these approximate counts are given using the hyperloglog. I mean, it is so efficient because usually you'll get like a 1 kilobyte sort of sketch. So let me tell you what I mean by sketch over here. So the way that the algorithm is going to work is, here's your stream. The algorithm maintains what is called a sketch. So a sketch is like a really small, very, very small, a small summary. And every time a new element comes along, the algorithm will update the sketch. So the sketch is going to be this small 5-bit or whatever, some small. You can think of it, in sort of abstractly, one can think of it as a data structure, but it's convenient really to think of it as a sketch, because you'll see that the updates to this, it's almost like a particular number or a quantity rather than a more complex object like a data structure. So it's going to maintain a sketch. And indeed, the notions of algorithms maintaining sketches goes back to Flageolet Martin, who introduced many of these ideas in streaming algorithms. And sort of as a historical point, it is often also associated with Alon Matthias Szegedy. Although Alon Matthias Szegedy was a paper in the 90s, Flageolet Martin is an earlier paper which really introduces these ideas of sketches. Okay, so now let's get into the details of what is going on. So let H, which is, I'll say n to, for now I'll just say that it maps, H maps the universe to an n bit, to a string of bits. So H, the hash function, maps elements to a string of bits, and H is a truly random function. So the way to think of this is we could interpret h as, let's say, a function to this just by truncating the bits to s bits. And this function is a truly random function. So the way we're going to say this is, imagine that h is actually for every n is going to randomly choose one of the outputs. Right? So you can think of, for every I in n, h of I is randomly chosen in that. And you can imagine that this is done at the very beginning, before anything starts. So all the probabilities are over the randomness of h. And this is also, in theory, one would then construct these h using specific families, and often then the math will continue. But here all the probabilities are going to be over the randomness of this function h, where for each I in n, h of I is randomly chosen amongst the output, and the output you can think of as an s-bit string. And for now, let's not worry about what exactly s is. You can think of s is going to be at least size log n. Right? S is going to be at least log base 2 of n, and we'll see that it's not going to be particularly relevant for us what s is. So you can think of a cryptographic hash function, and you're going to get some really long sort of hash value. Okay, so now I'm going to define a very important quantity. So I'll say for I in n, r of I is the number of trailing zeros in h of I. So if you take r of some number, so you take r of 42, you get some long sequence of bits, and r of 42 is now 3. So you simply look at the bit string that you get, and you look at how many trailing zeros are there. Okay, and the important fact, given the randomness of this function, is that the probability that h of I is more than L, that h of I is more than L. So that means that there are at least L zeros. So here's your string. Here's h of I'm sorry, I should say r of I. Yeah. So here's h of I. And so here are the L bits. And for it to be, let's just say, greater than equal to L, all of these need to be 0. Right? Maybe there are more zeros beyond that. And so this is exactly equal to 2 to the minus L. Okay? All right. So now here's the PC, the probabilistic counting algorithm. So the sketch is simply the maximum value of r of I seen so far. That's the sketch. Okay, so I'm going to so just to write it out formally, I'm going to sort of the zeroth step, the initialization is to initialize. I'm going to initialize this random variable z that I call 0. Then I'll say for every I in the stream, you compute r of I. This is easy. Then we simply set z to be the max of z comma r of I. Okay, does that make sense? So we're going to initialize z to be 0. Then for every object I in the stream, and let's just assume the stream is non-empty. Just this is going to be convenient for some of the quantities that I'm going to write. So for every I in the stream, we compute this Ri. So Ri is the number of trailing zeros in the hash. And then you just set it to be the maximum R value seen so far. Now note that repeated repeated occurrences of the same element do not affect z. This is important. So if you see the same element over and over again, nothing is going to change because you compute the hash value of that element, and clearly that cannot change the value of z. So repeated occurrences of the same element do not affect z. What is our estimate going to be? So finally, this is a very simple sketch. So the nice thing is this sketch it's sort of composable, meaning that if your stream was divided into multiple substreams, you can compute this independently for each substream and then combine these. So this is a combinable sketch. Right? Does this make sense? Because all you're doing is you're maintaining the maximum value. So if you have a collection of sketches, you can just take the maximum amongst those. Okay? And what we output, so I haven't, the final output is just simply going to be 2 to the z. This is the estimate of the number of distinct elements. So any questions about the algorithm itself?
Well, maybe slightly tangential, but if you wanted to, let's say you had like really big data, and you wanted to instead estimate like a loglog of the number of elements, is there an obvious way to modify the algorithm to do that?
You want to estimate the, well, okay, so again, you have to be careful. Like, to estimate, the thing is, if you estimate the log, and if you can estimate that accurately, that's going to lead to a much larger error in the actual estimate because you're exponentiating. And so if you estimated the log, then you're doubly exponentiating, in which case your errors are going to be much larger. It doesn't answer your question directly, but just saying that why you wouldn't do this over and over again. Now, so it's known that you can't improve on log. You can't go one step further. Now, if you wanted to say how are you going to estimate the log, you could try to treat your stream as a stream of Ri values, and then potentially you could try to use that in some way. But you'll see that even this, I mean, clearly, this is going to be off by at least a constant factor because, the output in this case is always a power of 2. And obviously, the number of elements doesn't have to be a power of 2. Right? So this is, there's going to be some error over here. Okay, So sorry. So does the sketch make sense? Any questions about this? Okay, so let's go ahead and analyze the sketch. The analysis is not particularly hard. Like once you write things down, or I should say, the very basic crude analysis is not hard. An exact analysis of this was a significant tour de force by Flageolet and Martin. Okay, so as we said, the probability that R of I is greater than or equal to L is 2 to the minus L. So let XL be the indicator for there exists some I in the stream such that R of I is greater than L. So just the indicator for this event, for the existence. So what's the probability that XL is equal to 1? We can write this as 1 minus 1 minus 1 over 2 to the L to the power D, where D is the number of distinct elements. Now, here I use the fact that the hash values are all independent, right? So this event here, so the probability that it's equal to 1 is just the probability that one of these events happens is the union over I of R of I is greater than L, right? Which I just write as 1 minus the probability of the intersection of R of I is strictly less than L, and then use independence. And so similarly, the probability that XL is equal to 0 is really simple. It's 1 minus 2 to the minus L to D. Okay, so now let's ask, what is the probability that Z that was output, the final Z, is greater than equal to the ceiling of log base 2 of D plus C for some constant C. So C is going to be some constant, some small constant. What is the probability that Z is greater than this? So this is clearly the probability that X log base D plus C is equal to 1. Okay, now let me just plug in the formula. So I'll say 1 minus 1 divided by 2 to the log base D, log of D plus C to the power D. Okay, and now I'm just going to use a binomial approximation, and what I'll say is that 1 minus x to the power D is greater than or equal to 1 minus dx when d times x is less than 1, and that is clearly the case here because x is this quantity here. And so I have a lower bound on 1 minus d to the x, so then I can upper bound this by d divided by 2 to the log base d plus c. And so what I get here is just 2 to the minus c. So the probability that my final output is going to deviate from log base d plus a few extra bits, right? A few extra, sorry, bits is the wrong word, but by even by 1 or 2. So the probability that the estimate of log d is off by even a constant, it goes down exponentially in that constant. Okay. Then let's say, what is the probability that z is less than log base d plus c, minus c, minus c. So this is the probability that x log of d minus c is equal to 0. So plugging this in, I get 2 to the minus log base d plus c to the power d. Now I use my favorite approximation. 1 minus x is less than e to the minus x. So I get this is at most e to the minus d divided by 2 to the log base d times 2 to the c. Right? And I can write this now as this is most e to the 2c minus 1. Okay, any questions? It's a relatively simple analysis.
Should it be minus c? Like the second term after the probability?
Here?
Sorry, above.
Here?
Yeah.
No, so the minus is, yeah. Sorry, I did I apologize. I did too many sign switches here, but you see that essentially as c increases, this probability decreases, actually in this case doubly exponentially, and this probability as c increases decreases exponentially. So let's just, again, because we're doing sort of a very rough back of the envelope calculation, suppose you set c is equal to 2. So what you get is that the probability that x, I should say the probability that z is more than log base 2 plus 2 is at most 1/4. The probability that z is less than log d minus 2 is at most e to the minus 2, which is like 1 over e squared, and this is definitely less than 1/4. It's actually much smaller, so we can say it's less than it's less than 1/8. So by the union bound, the probability that z minus log d is less than equal to 2 is at least, so does that give you a 1/3 probability of error? So it's 1/8, 1/4. Yeah, so this is at least 2/3. Okay, so this means that this approximates. We get an approximation for log d up to 2 bits. Up to 2. I shouldn't say bits. I should say up to 2. Now, what this means is that 2 to the z is between 2 to the log d times 4 and 2 to the log d divided by 4. So we get, and 2 to the log d is off by a factor of 2, so very crudely we get an 8 approximation to d, with probability at least 2/3. One can then use standard boosting, the median. One can use the median trick to improve. And the storage. So we only have to store z, have to store z. And we know that z is essentially going to be less than log d plus some constant c. In this case, it's going to be plus c with high probability. And so the storage is going to be the log of this, is at most log z, which is essentially log d plus some constant. And this constant is tiny. So typically this is, you can just think of this as really going to be at most log n. So it's just quite remarkable. Now you might say, well, it's an 8 approximation. That's not great. But it's just log n bits. Right? It's a tiny sketch. So you're looking at 2 to the 32 elements. You're storing essentially something like 5 or 6 bits. And you're still getting, a reasonable, an order of magnitude approximation. And our analysis was sort of crude. So, maybe you could tighten this somewhat. So does this make sense? It's sort of deceptively simple, but it's an amazing idea. It's an amazing idea. Any questions?
Question.
Yes.
I was just wondering, how much would the base of the log affect the analysis?
So the thing is, the base of the log affects the factor that you get there. So actually by quite a bit. But if you only cared for a constant over here, then it doesn't matter. But if you care for what constant you get, then it does matter.
Okay, thank you.
Right? Because you're exponentiating what you finally get. This still leads to the question of, so what is the expectation of 2 to the z? So we did this sort of crude analysis. We know that you can sort of push this further to, if you follow this, you can prove that the expectation of 2 to the z is like some O of 1 approximation of d. Like we just said that this happens with high probability, but you could work out the expectation. You can work out some bounds on the expectation using this math. But in a Flageolet-Martin, and this was actually one of the main contributions of their paper, they basically showed that the expectation of 2 to the z, it sort of tends to there's some very specific constant that they give, 2 to the, I think it's like 351 maybe, times d. And this is sort of a limit as d goes to infinity. There's a rapid convergence of this limit. Convergence of the limit. And remarkably, this is a tour de force. It uses complex analysis to prove this, and it's a highly non-trivial proof. I mean, I have not gone through it myself in any detail. So it's a very significant result, and it uses complex analysis. It's considered really a tour de force of. And so in practice, what you can do is you would essentially divide 2 to the z by this magic constant that they provide, and you get an estimate. And this is an eminently practical algorithm. So this is a remarkable result. So they could actually, they pinned down what the expectation of probabilistic counting is, and this is referred to as the correction factor. So this leads to sort of a very interesting divergence in the viewpoints of the theory world versus, let's say, those, as Flageolet Martin would call it, they call it the analysis of algorithms, which is sort of in between pure theory and practice. Their aim was to actually give a practical algorithm which had a mathematical backing, and so this is the algorithm that they gave. In the theory world, this requires assumptions of hash functions which are very strong, and so there the results went down a different route. So let me tell you about, so maybe I'll come back to this point towards the end of the lecture on Flageolet Martin. This is the basis of the hyperloglog algorithm, and I'll tell you a little bit more about how hyperloglog works. But first, let's go to an improvement, the theoretical improvement. This is given by Baryosef, Jairam, Kumar, Sivakumar, and Trevisan. Now this was given in 2004. So this algorithm is going to give a 1 plus epsilon approximation to D. Okay, so I'm sort of fudging what they're doing. This is an improvement in the realistic model. So let's stick to the realistic model, where you have these truly random hash functions. Now, of course, if you had truly random hash functions, then you could just do this. But I want to sort of tell you the main idea in Baryosef et al. Without getting into the specifics of the hash functions they do, which I will defer to the next lecture. So they give a 1 plus epsilon approximation to D in storage, which is essentially O of epsilon to the minus 2 log 1 over epsilon plus epsilon to the minus 2 log n. So they get the log n dependence, and they say, well, if you're willing to give a 1 over epsilon square, then you can actually get a 1 plus epsilon approximation. And even though this is not in the theoretical model, one can generalize this to the theoretical model with an additional term, and again, I'll talk about this in the next lecture. So what is the idea? And the key idea is to say that, well, if you look at the problem, or if you look at the weakness in our crude analysis here, the crude analysis here, we have to set C to be some constant. And even if we set it to be 1, or even if we set it to be 0, we still have this, once we set the constant to be 1 or 0, the probabilities we get here are too large. Also, we have to deal with, the floor, and this is going to give yet another source of approximation. And somehow the problem seems to be, that we're looking at these very specific events. And this approximation that I did here, is a reasonably good approximation. So there's not much that you can squeeze out. And so their idea is to say, so instead of tracking the largest Ri value, store the R such that sufficiently many I have Ri greater than equal to R. Sorry, yes, sorry. So instead of tracking the largest Ri value, you store an R such that sufficiently many objects have an Ri greater than R. And this ensures better convergence. This ensures better convergence. So, we need some, we need some care to sort of store everything. So let me tell you how this is going to work. So we're going to use two hash functions now. We use two hash functions. So we'll use h as before, right? And this is used to define the R of I. We're going to use another hash function which actually maps things to a fairly small space. So this is really a short hash. So it maps.
I have a question.
Yes.
So the flageolet Martin result says that the earlier algorithm is usually is going to be an under approximation for E.
Yes, but yes.
This algorithm is is lower than is always going to be lower than the other algorithm, right?
Which one? You mean the improvement?
That we're talking about right now.
Yes.
So how can it be a better approximation? I guess.
No, I'm going to give you a different algorithm. Maybe I'm missing the point.
Well, I'm saying that because we're using an RI value which is lower than the largest RI value. Right?
Yeah, so yeah, you'll see that but we're going to do much more than just take 2 to the Ri.
Okay.
Right, the previous algorithm just maintains this one value z and says take 2 to the z. Now I'm actually this algorithm is going to compute 2 to the z and then scale it with something else to make it a better estimate.
Okay.
Right, so something more is going to happen. Now what I want to emphasize here, okay, so maybe I should say this, I can mention this right here. Okay, so now it uses these two hash functions, and this G maps elements to essentially a random string of epsilon to the minus 4 log squared in bits. So this is another hash function. Okay, so now let me come back to this theory versus practice gap here. So flageolet Martin assume hash functions are truly random, and this of course leads to the result. Now Baryosef et al. Only require pairwise independence in the hash function, and this is also referred to as two universal hash functions. So they only require pairwise independence, so they require much weaker assumptions. So if you assume the hash functions are truly random, then you can just use flageolet Martin, you use probabilistic counting, we have a correction factor, we get an unbiased estimate. Baryosef and al. Only require pairwise independence in their algorithm, so this is a weaker assumption. This requires two universal hash functions, and we know how to construct these. We know how to provably construct these. Now, in the analysis that I am going to do, I am actually going to assume full independence just to make things simpler. And I will show you that you can also use pairwise independence. And the next lecture, I'll actually discuss how you construct such hash functions. It's not very complicated, but it's a useful exercise, probabilistic exercise to do. Okay, so having said that, with all that prelude, let me now tell you what the algorithm actually is. Okay, so now this is the algorithm. So previously the hash was this single number. Now the hash, or the sketch, the sketch was a single number. Now the sketch is a set called B and a value Z as before, and B stores all elements I such that R of I is greater than Z. So it's going to have some value, and the Z is very similar to the Z that we had before. Now previously we just stored the maximum. Now B is going to store some other value. It's not going to store the maximum. It's going to store a smaller value, but it's also going to store all the elements I such that Ri is greater than Z. Now storing an element could be expensive. So we store G of that element. And G of that element is much smaller. Right? So the key is, instead of storing all these elements, we store the hash of these elements. And now we have to be careful that this hash is going to work the way we want. Okay, so now let me write down the algorithm. I'll talk through it, and then we can do the analysis. So now I'll say the sketch is now to process element I in the stream. To process this element, what we'll say is, if R of I is greater than Z, only then are we going to do something. We're going to update B now. I'm going to say B union. Now B is going to store a collection of pairs. So it's going to take the hash value. It's also going to store that R value. Right? So B stores pairs. The hash value under G and the number of trailing zeros. Right? So it's a union. So if this element is already present, then of course nothing happens. It's a union. And now here is the key. Say while B, the size of B is at least C over epsilon squared. C is going to be some constant here. We will update Z. So we increment Z. And then we remove all pairs such that, so I should say all pairs G of J, R of J, such that R of J is less than Z. So this is the algorithm. To process an element in the stream, you first check, is the number of trailing zeros more than Z? If it isn't, then you just ignore the element and move on. Otherwise, if the number of zeros is more than Z, then you insert Z into your bucket. You insert I into your bucket. except you store I through its hash value in G. So you store I through its hash value in G, and you also keep track of what its R value is. Then
For the pairs in B, if G of I is not distinct but R of I is distinct, are those treated as separate?
if G of I is not distinct, yes, you will treat them as separate. You will treat them as separate. You'll see that this is not going to be an issue, but yes, you treat them as separate. Right? This is just it's a set of pairs. Now you say, while B is sufficiently large, so let's say B is larger than C over epsilon squared, so it crossed some threshold. Then you increment Z and you remove all the pairs whose R value is less than Z. So this is going to maintain your size. Okay, so what is the storage going to be? The storage is really the size of B times size in bits of each element of B. This we ensure is at most C over epsilon square. The remaining, well, we have to store G and we have to store R. Now storing R, this is log n, as we discussed earlier. To store G, G maps it into a universe which is essentially epsilon to the minus 4 log square n, and so what we need is log of this. That's how many bits we need. And so what we get over here is we get log of 1 over epsilon plus log n. So this is C over epsilon squared times essentially log n plus log of 1 over epsilon as desired. I still haven't told you how to produce the output. I'm sorry, yes?
Is storing Ri just like an efficiency of lookup thing?
It's just an efficiency of lookup, right? So that you don't have to recompute the hash function. Right, you could, I guess what you're saying is you could always recompute the hash function here. Well, not entirely. You don't really know the element.
Zero.
I'm sorry?
If we're storing the hash, we can just recount the...
We're not storing the hash. We're storing a different hash.
Oh, okay. I see.
Right? Remember that Ri is defined with this Hn. You should actually think of Hn is going to actually map n to n. So the hash of H could be extremely large. It could be as large as log n bits. So you don't want to store the element itself. You want to store some compression, but you have to be careful because the compression is going to create collisions.
Got it.
And now I have to tell you, what is the output going to be? Right? The output. So the output is going to be the size of B times 2 to the z. This is going to be the output. The size of B times 2 to the z. Okay, so remember that the algorithm stores a value z and a set B. B is going to be a set of pairs. To process an element in the stream, it's going to first look at the number of trailing zeros, that's R of I. Now, R is computed with respect to the hash function H, not G. And H, we should think of as a hash function that maps, log n bits to log n bits. G maps log n bits to actually log of these many bits. So it's this was a mistake. It's really to log of that many bits. So H is going to be your usual hash function. This is your whatever cryptographic hash function. It's a large hash. You do not want to store the entire hash. So to process an element, first you check the number of trailing zeros. If it's less than z, you ignore it. If it's more than z, then you store the element in B, you store it with its hash value in G. You also store its number of trailing zeros. This was again with respect to H. So now that you've stored this, if the number of pairs crosses a threshold of C over epsilon squared, some constant, then you increment your Z and then you throw everything, you remove everything that's going to be less than Z. Your final output is going to be the size of this bucket times 2 to the Z. So I'm going to pause here and I'll take any questions, and after that I'll continue with the analysis. Okay, so now on to the analysis. Now there is a particular calculation that I am going to leave as an exercise. Now note that, roughly speaking, at any point there are at most C over epsilon square elements seen so far with R of I greater than Z. By randomly mapping to a universe C over epsilon to the 4, C square epsilon to the 4, I'll say times log n, by birthday paradox. Okay, that's where the 4 is coming in, because the 4 is the square of this, and the extra log n is going to be so that we can do a union bound. By birthday paradox, the probability of two such elements, by such I mean the elements with this property, the probability of two such elements having the same G value is going to be much smaller than 1 over log n. This is the birthday paradox calculation that you'll need to do. You're mapping it to a universe whose size is essentially like n squared. So you're taking n elements, or I shouldn't say n, that means you have k elements, mapping it to a universe which is k squared times log n. And you're saying, what is the probability that the two elements will map to the same hash value? Remember, this is the G, the random mapping here, this is G. This probability is going to be much smaller than 1 over log n. And you get a 1 over log n because that's exponentiating this quantity. So this is an exercise. It's a somewhat more challenging exercise, but you can work it out. And so by union bound over all values of Z, we can union bound over the all log n values of Z. G never creates collisions in B. I've written this, sort of gone through this really quickly. You want us to do it carefully. But the concern that was raised, like, what is the point of G? Remember, we couldn't really store I. We had to store G of I to save space. What we're arguing is that because G maps to a sufficiently large universe, we are guaranteed that there are no collisions here. So if you have two different I and I prime, both of whose R value is more than Z, their G values are likely to be different. G, instead of never, I should really say with high probability, never creates collisions in B. So is this point clear? So please ask me questions, because this is a sort of subtle point that I am leaving the calculation as an exercise to work out the details. So I am going to assume, let us assume that B stores I directly. So we're going to assume here that B, instead of storing this pair, is simply going to store I directly. And if it stores I, remember all of this can be done. So instead of storing pairs, it's actually just storing I. Okay, so I want to think of what B is doing is just B union I. Now we cannot do this in general because it takes too many bits to store I. But we are assuming this in some sense with non-trivial argument because the hash function is large enough to prevent any collisions. Okay, let us assume that B stores I directly. So any questions about that? This is a tricky point. So I'm willing to explain it more if you need some clarity on this.
I'm a little bit confused about C.
About sorry, which part?
C.
The constant C?
Yeah.
Confused as in it's just some constant that I'm going to put in there. Is that, I mean, oh, you mean what is it? Like think of it, it's going to be like 20 or something.
Okay.
Yeah, it's just some absolute constant, yeah. So I'm going to assume that B stores I directly. Okay, so now let's do the analysis. So XLJ is going to be an indicator for the event R of so I'll say I, that R of I is greater than or equal to L. Right? This is just looking at the indicator for the hash of I having L trailing, at least L trailing zeros, and we know that the expectation of XLI is 2 to the minus L. Y of L is going to be the summation over XLI for I in the stream. And so the expectation of Y of L is D times 2 to the minus L. This is an indicator for each I, whether Ri is greater than or equal to L. This is the sum of indicators. Okay. Now what is our estimate? Remember, estimate was 2 to the z times b, and because we assume that b stores I directly, this is the same as 2 to the z y of z. Right? Y of z is the number of I such that Ri is greater than L. And that's exactly what B stores. It stores everything whose hash value is or whose R value is at least Z. Okay? So now let's look at, we are interested in the probability that 2 to the z yz minus d is at least epsilon times d. That's what we want to look at. Now we can write this as the probability that yz minus d 2 to the minus z is greater than epsilon d times 2 to the minus z. This is precisely the expectation of yz. Okay, so this is looking like good news here, because again I can just write this as, this is the probability that yz minus the expectation of yz deviates more than the expectation, epsilon times the expectation of yz, which is looking a lot like our Chernoff, Chebyshev, whatever our deviation bounds. Seems like we can do something interesting here. And of course, by the Chernoff bounds, remember these indicators, they're all independent. So by the Chernoff bound over here, we could say this is at most 2 times e to the minus epsilon square expectation of yz divided by 3. Now we're going to have a bit of a problem here, or actually this is, we need to, for this to work, we need the expectation of yz to be sufficiently large. And in some sense, z was specifically chosen so that this expectation is likely to be large. And that's sort of the whole point here. Except we have to be a little careful here, because we chose z so that empirically we saw many objects, whose trailing zeros is more than z, and here we have the expectation, so we need to be a little careful with the math. And so now let me just rewrite this and just simply say that the following should be true, that for all L, the probability that y of L minus d times 2 to the minus L being greater than epsilon d times 2 to the minus L, this is at most epsilon square the expectation of yl divided by 3, but the expectation of yl is precisely this quantity here, and so I can write this as, this is whatever this is at most, to the expectation d 2 to the minus L divided by 3. Okay. Okay, so now what I'm going to say is, if d times 2 to the minus L, if this quantity is greater than, let's say, epsilon square, let me make sure I get this right, is at most, say, 20 over epsilon square, we get concentration. Then what we'll say is the probability that d times 2 to the minus z is less than 20 over epsilon square is very small. Thus, d times 2 to the minus z is going to be greater than 20 over epsilon square, and the probability and sort of with high probability, d times 2 to the minus z is close to its expectation. But this is exactly d times 2 to the minus z is exactly the output, right? So that means implying the output is close to its expectation, which is d. Remember, the output was 2 to the z times yz. And so if yz is going to be close to its expectation, which is d times 2 to the minus z, multiplying them together, then the output is going to be close to its expectation. Now, because this is sort of the last few minutes, I'm not going to work this math out in gory detail right now, and I'll do it in the next lecture. So in the next lecture, when we continue, I'll just redo this analysis, I'll finish it up, and then we'll discuss more about two universal hash functions, some comments on the hyperloglog, and then proceed on from there. So I'll end over here and I'll take any questions.